We are live. So good morning, everyone. My name is Jesse, and I am part of Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And we are really excited because all October long, we have been celebrating Space Month. So by the end of the month, it'll be over 65 sessions with amazing people from around the world, over 45 of those with space researchers, engineers, astronomers, astronauts, and more. So it's a really exciting time for us, and we really appreciate you guys being here as part of it. So right now we've got two classes from across North America joining us. I want to give them a chance to say hi. We've got Miss Woods, grade 6s in Bradford in Ontario. Hi, guys. Hey! And we've got Miss Saunders, grade 5, 6s in North Bay, Ontario. Hi, guys. Hey! All right. Of course, the reason you guys are all here today is for our speakers. We are joined live in London, Ontario by Dr. Parshati Patel. So she's an astrophysicist and science communicator for Western Space, the Center for Planetary Science and Exploration. And she's going to take us on a little bit of a tour through the universe, understanding a little bit about what drove her to do what she does today, and then a little bit of an extra thing at the end, which you guys you'll be excited about, and I won't spoil. So without further ado, thank you so much for joining us, Dr. Patel, and take it away.
Thank you, Jesse. I'm so excited to be here, guys. I'm looking forward to a lot of your questions. So what I'm going to do is I'm going to give you guys a quick spiel on what I have done in the past few years, and then kind of give you a quick overview of what I do right now. So I'll start with a presentation, and then we'll take questions after. So I'm just going to share my screen. So is everyone able to see this?
It's perfect. You're great.
Awesome, perfect. So as Jesse mentioned, I am an astrophysicist and a science communicator. And so I started off, just wanting to study space. And so I'll give you a little bit of a background of how I got to where I'm today. And you will see maybe in your journey through life, you will probably get inspired by, tiny things that you may not even think that they would inspire you. So when I was very young, I went on a vacation. So I'm originally from India. And so my parents took me on a vacation to Mumbai. And one of the tourist things to do there was to visit a planetarium. And because there was none in my city, I actually ended up, seeing, kind of learning about the wonders of the night sky for the first time in a planetarium. And I was around 12, 13 years old. So, I was kind of getting at a point where I was learning all about the universe through this planetarium. And after the show, I actually got really excited and asked my parents, how can I learn more about this? And I had so many questions and I couldn't stop asking questions. So they decided to actually get me books. So I ended up, getting tons of books from the planetarium itself. And I spent the next few months just reading all those books. This is definitely not my stack of books that I bought at that time. This is just a picture. But I come from an era where I didn't own a camera to be taking those pictures of the books. But I still actually have those books, which is very interesting. And what that did was, it let me ask more questions. It led me to discovering these new areas of astronomy and space that I did not know about. And I think at that point, I was interested in history, geography, biology, and all these different aspects, not just particularly space. But I think what kind of decided that this is what I was going to do was my a gift my aunt gave me. So my aunt was visiting me from Canada, and she decided to gift me a small telescope just like this one. And it's not very big, but for someone who's 13, 14-year-old has their own telescope. And I lived in a big city with a lot of pollution, so all I could see was the moon, constellations, and it's Jupiter and Saturn sometimes. So the first time I pointed my telescope at the moon, I was like, oh my God, this is amazing. What if I could do this for the rest of my life? Just, looking at the night sky and learning about all these different objects in the universe. And obviously at that time, I wasn't sure what kind of, career one could have in this area. So I ended up researching a lot about what I could study, where I could go. And so I ended up in Canada going to University of Toronto for my bachelor's in astronomy and physics, and then ended up here at Western University doing my master's and my PhD. And I was always intrigued by how planets and stars form. It was a topic that drew me from the start, I think probably because we live on a planet and we have a sun that's close by, and I always wondered how things formed. So today I'm going to tell you a little bit about what my PhD thesis involved, but you may have seen the title of my presentation was A Stellar Detective. So in addition to being all, into the sciences, I always wanted to be a detective. And for me, it was all about crime scene and kind of investigate and finding, the clues and figuring out the mystery. And so, I still call myself a detective. It's just now I studied stars. I call myself a stellar detective because I'm now studying, these stars that have this own mystery that I'm trying to solve. So I'm going to take you through the process of this, how do you find a mystery? What are the things that you can, use to solve these mysteries? And I'll take you through the steps of how I, helped in solving some of these mysteries that intrigued me. So let's start. Let's start with an amazing picture of the star forming region. So these are two of my favorite regions where stars actually form. So these two regions, the Orion Nebula up here and the Eagle Nebula right here, these are places where it has the perfect ingredients. It is the dust, the gas, the amount of energy that's flowing through this region to form stars. So what you're seeing, all these dots here, are actually these massive stars that have formed in these region. And somehow my slide changed. Sorry about that. And what you're seeing is this pillars of dust here. And these dust are kind of crucial in forming these stars. And what you see in these squares right here, so I'm pointing using my mouse, these are actually stars that have already formed, and we currently actually own, have these technologies that allow us to not only look at these big areas where stars are forming, but actually hone into the areas where stars have formed and actually take pictures of those. And so, I just by looking at these areas, it's so exciting and it's so mysterious that what I wanted to study were these young stars and how they form in these chaotic yet beautiful, magnificent areas of the universe. So, when these stars, if you look very closely, this is what they look like. This is not a real picture. This is what we call an artist's conception of what it would look like if, let's say, you had a spacecraft that would let you fly through these, star forming regions and get you to this one star that's forming right now. So what ends up happening is you have a lot of gas and dust. It's going around. You have a lot of shock waves that are going through. They allow these material to clump together. And as they do, gravity starts pulling things together in the center. So what you're seeing on the screen here is actually not a star. This is just before the star actually forms, where you have this central object that is just gathering all the material onto it. And it's generating this energy that is, in form of light and these two lovely jets that you are seeing. And so it goes from like a cloud to like a pancake almost. and this is the pancake of dust and gas. And so that actually does not allow us to see what is happening on the inside. We don't know how this star is forming. All we are seeing is this light and this dark gaseous disk or dusty disk, depending on where you are. And so my slides keep going backward instead of forward. It's interesting.
One of those mysteries of the universe.
I know. So in the past, we have the amazing Hubble telescope. It has actually taken around 200 pictures of these really, really young stars that are forming in the Orion Nebula. And some of them are, on here on the screen. What's interesting to see is like the wide variety. Some of them have, a single tail, like the one here. Some of them just have a dark disk and you cannot really see what's going on. Some of them have, this cloud of gas and dust around it. So, they come in wide variety, but at the same time, there's similar stars that are forming. So my mystery was to kind of find this, one topic that really interests me and try to solve how these stars are actually forming when they are. So, if we kind of do in the nutshell, it goes from a cloud to a disk, and disk with a central star that is not yet a star. We call it a protostar. And so it is very much on the verge of becoming a star, but at the same time still creating material from its surrounding. And so, when we look at our solar system, we see the sun, and then we see all these planets. We don't see any of this dust or gas. A lot of this dust actually in the picture that you see here ends up becoming those planets that, one of which we live on. And then a lot of the dust and gas kind of dissipate away. And then you are left with a star and some planets, sometimes just a star by itself. And so when I was trying to find this one particular mystery to solve, what I was really looking forward was to study how this material gets onto the star and what is the process that actually happens, because we're not really able to see it. Unlike other sciences, for example, biology, you can actually go to, your subjects of study. Could be bacteria, could be animals, could be birds. For astronomy and space, it's so vast, you cannot just travel to the place that you want to study. And that's actually what makes it more interesting than anything else, is because you are sitting here on Earth and trying to study these things that are so, so far away. And so to find my mystery, I was looking at all these different kinds of stars. And it's interesting to know that our sun and other stars actually come in very many different flavors, as I like to call them. And that's because they come in very many different sizes. And so, they're named alphabetical. It's not alphabetical order, but they're named using alphabets. And you will see over here, you have M class, which is very, very tiny, very, very red star. And there are two scales. So if you were to put like a G-type star, which is what our sun is, and compare it to an O-type star, which is right here in blue, you will see how big the O-type stars are. And what makes it really interesting is the bigger the star is, the higher the surface temperature. So our sun is around 6,000 degrees. Your oven is around 400 degrees. So the most massive stars could range 30, 40, 50,000 degrees on their surface. So they're really, really hot. And, if we say our sun is unique, it's not really unique. There are tons of stars like the G-type stars. There are tons of stars like O and B-type stars. What I was really interested is actually understanding these massive stars, so the B and the O-type stars. And the reason for that was these stars actually, because they're more massive, they actually die faster, which is interesting. Another interesting aspect is the more massive you are, the more fuel you're going to use, the more faster you're going to die. And so there's a very, very small amount of time that these O and B type stars actually take to form. And so that intrigued me because it's a short time scale that we are looking at. So I found the mystery. I wanted to study these B and O type stars that actually end up, being these mysterious objects that we don't know how they form. And so for the mystery, I kind of honed into this one particular region in this star. So let's say if I take a donut, cut it in half, and if I look at the donut from sideways, this is exactly what I'm doing in this picture, is I took the star plus the disk and I cut it in half and I'm looking at it sideways. And so what you see is, you see a tiny object in the center, which is what will eventually become a star. You have a gas around it. There's no dust in this region because it's so hot that the dust actually evaporates and there's nothing left. Okay. And then as you go further away, you start seeing more dust and these are the regions actually where the planets end up forming. And a lot of people study that region because, planets, amazing. What I really wanted to study was something people were not concentrating on, was this lovely gaseous area. This area, because there is no dust, and this is actually crucial in how the star is actually forming, I wanted to learn more about it and what it takes to form that region and how it impacts the formation of planets and the star itself. So now that I had my mystery, I obviously have to go and find a way to solve it. So one of the things I had to do was to look for data. First of all, if someone did actually any work in that area, then I would have to study that. Look if someone has studied any stars like these. If so, what did they find, right? And then if there is nothing, there was hardly any work in this area because, you know, what I was doing was something no one had done before. And that's very, very hard at first because no one has anything on it. But at the same time, it allowed me to then go and get more data. So that was kind of my first step. So I went and got more data using telescopes like the Canada, France, Hawaii telescope in Hawaii. I, got to apply and get some time on it. So now I can actually take some data, basically is a light from these stars, and analyze them for what material is present there and how it's impacting the star. So to do that, what I did was I took the data that was given to me from this telescope, and if I were to lay it out, this is what's going to look like. So I'm assuming all of you have seen a rainbow in the sky, right? So, okay, so what I do exactly is very similar to that. What happens is you take the light from the star and you use something that actually creates this rainbow. And this is what you're seeing on the screen right now. What's very interesting and what we don't see in our rainbow is these dark, patterns that you're seeing. So I'm going to move my mouse to one of those. You can see this one right here. It's consistent throughout. These are all different stars that we are looking at. So each of these panels is a different star. And so each of these dark band that you are seeing is actually a fingerprint for elements that we see in these disks. And so I can take that, I can take, a particular star that I'm studying and then analyze that particular band. And so this is what it's going to look like. We don't really need to go into a lot of detail, but I'll tell you what exactly I look for. Okay, so I take that data and then now I process it. And so this is what it's going to look like. So don't worry about all the numbers and stuff like that. What I really want you to kind of gather your attention to are these lovely peaks here. So the first one that I want your attention drawn to is this peak right here. All of these bumps that you're seeing, they're basically, a signature of these different elements. And this particular one that I showed you right here tells me that there is hydrogen present, okay? The ones here at the bottom are actually calcium, oxygen, everything kind of what we see here on Earth, including iron, right? So I know now that there are all these material that's present. What do I do with this? Like I have the data and I know that all of these materials are present somewhere in the disk. What I now get to do is go back and think about what I know about stars and develop a theory on what is happening there. And the way we actually do it, we are very lucky to be living in a time when we have these computers and supercomputers that can allow us to develop almost entire universe in your computer. So I actually got to, come up with a computer model that actually has a star. And I come up with what the star looks like, what the size is, what the mass is, temperature is, and put a disk around it to see if I can, somehow simulate what I'm seeing in the sky. So here is a picture of that exact computational model that I'm using in my computer, where I have a star in the middle and a disk around it. And this is what it would look like if, I were to drive my spaceship and kind of anchor around it to see what is happening to it. And what I now do is, I have the computer model that looks like similar to what I think the object in the night sky is. And then I take the data that I had before and then compare the two. So that's, this is something that allows me to figure out whether or not my understanding about the stars is correct, because now I have data that I can compare it to. So once I do that, I can actually test my theory and go back to figuring out if I was able to solve the mystery. If not, we go back and figure out what was the issue and kind of do the same cycle all over again. And this is kind of one of the cycles that you do almost on everyday basis with all, whether it's the data that you have, whether it's simple, mystery that you're figuring out whether the temperature of that star is correct of what I'm putting, to whether the data that I have is correct or not. So you go through the same cycle every time when you're trying to figure out each and every small slice of the bigger mystery. So that's kind of an overview of almost like my 4 years worth of work in a very short amount of time. But as Jesse mentioned, I'm also a science communicator. So now my job is to kind of communicate what we as scientists do on everyday basis to everyone. Doesn't just have to be students, to public, to anyone who's interested. So one of the current programs that we are currently working on is called Junior Astronauts Campaign. I'm sure many of you would want to be an astronaut. You could also be an astrophysicist or many other professions that actually help us to study the universe. This is a Canadian campaign. It was run by Canadian Space Agency. What they're trying to do is to bring awareness about what different kinds of careers you could have in this industry, but also at the same time, just getting you excited about what Canadians have contributed to space in the past and will in the future. Many of you will be in the workforce by the time we have the Lunar Gateway, which Canada is proudly part of. I don't know, one of you might actually be one of those people working on those lunar gateways when you grow up. So, for educators, I would say, please go ahead and look at this campaign. There are activities that students could actually do in classroom. And if you do at least one, you can get your name to put in the draw that can win you a trip from an astronaut at your school. So that is super amazing. But at the same time, if you're a student and you complete at least one activity in 3 of the streams that they have, you could be one of the students that actually go to the Junior Astronauts Camp next summer at the Canadian Space Agency headquarters in Quebec. So, there are amazing things to not only learn about what it takes to send an astronaut to space or study space in general, but at the same time, just to learn about what Canada has been doing for past so many years in the space domain. So I would love to answer any questions you guys have now, and feel free to ask me both about the Junior Astronaut Campaign and the stuff I talked about before.
Very cool. Well, thank you so much, Dr. Patel. And then we've got 2 groups watching on YouTube Live as well. So if you guys want to type in questions in the chat bar, just let me know where you're joining from. I'll share some questions. Parshati, if you could come out of your screen share, that would be great. I know we've got junior astronauts up, but I will share that with our classes at the end too, so you guys can learn more. But it's a really fantastic campaign, and we really encourage you to take part as well. It's a lot of fun. And both our classes today, grade 6, so that's perfect. A question to kick us off, because you mentioned it a couple times in the junior astronauts thing. What is the Lunar Gateway before we dive in with classes?
Yeah, so a lot of people know about the International Space Station. So what we want to create, so we all want to go to Mars. A lot of people talk about it, but our first step is to, learn and test our technologies, learn about the environment, and, do a lot of these testing before we actually get to go to Mars. And Moon is so close by that it's kind of our next step. So we have been on International Space Station for a while. We have had a continuous presence, and now it's to go to the Moon. We're going to have almost like an International Space Station kind of a station around the Moon that's not going to be actually inhabited by humans for a very long amount of time. It's going to be a few months out of the entire year. But for the rest of the year, it's still going to be doing a lot of science, and it's going to be all automated. So Canada is actually going to be part of this mission, and it's going to be supporting through AI, which is the artificial intelligence, as well as robotics. And so, we're really excited about our contributions to this, and looking forward to have something that goes around the Moon all the time and is doing experiments and helping us to get to Mars.
Very cool. All right. So yeah, let's dive in. We're going to start with Miss Wood's class. If you guys want to kick us off with a question, you are demuted. Come on up, guys.
Hi, Alex. You gotta speak a little bit louder.
Where do shooting stars go?
Oh, amazing question.
And what is a shooting star?
Yes, so I'm going to start with that. So a lot of you may have seen, sometimes in the night sky, either you're camping or driving in a countryside, just tiny streak of light that just goes through really, really quick. And you are like, I saw something, but maybe I didn't, right? Those are shooting stars. And what they are these tiny, almost size of dust, a grain size that you will find on the beach. So if you go to the beach, you find a lot of dust, and if you pick up just literally one grain, and you leave it to come close to Earth and have it go through the atmosphere, that actually burns up in the night sky, and that's because of the friction that it has with our atmosphere. And so what you're seeing is that streak of light that's actually the dust actually burning up in the atmosphere. Sometimes what happens is you get bigger chunks. And this is where you have something the size of a pebble or something bigger that can actually survive that flight. And it actually is more brighter, and it shines and lights up the sky for a little bit longer than the shooting stars, which are tiny streaks of light. And what ends up happening is, if it doesn't burn up completely, they end up on Earth, and they end up in what we call a meteorite. So these are rocks from space that end up and land here on Earth. And a lot of the times, people who study these rocks actually go and pick those up. And I don't have it here with me, but I actually do own a very, very small meteorite as well. And they're really interesting because those material are some of the most pristine material that you can get kind of handed to you, instead of having to go visit the asteroids and other objects in the solar system to get that material. And so those dust grains or tiny pebbles can actually come from places like the asteroid belt. Could be material that was created when materials collide, just like maybe two pebbles or two asteroids colliding. A lot of the times you may have a meteor shower month, or a time when there is meteor shower and you see tons of these streaks of light or shooting stars. A lot of those are results of cometary material, which is leftover material from comets when they pass by. And so, the origins vary, but they are basically leftover tiny material in the solar system that go through the atmosphere.
Very cool. And I actually pulled up a meteor shower while you were doing that. So the next one, November 16th into the 17th, is the Leonids, which is always a really spectacular one. So for both the towns that you guys are in, either in town or just outside of it, you can see a ton of meteorites, and I really encourage you to do that. If you've never seen a meteor shower, it's really exceptional. All right, Miss Saunders' class, come on up.
Hi, my name is Aria, and I was wondering, how often do stars form, and how long does it take for a single star to form?
Yeah, excellent.
Really good question. So stars actually form all the time. The process is very long. It takes millions and millions and billions of years for them to form, depending on their size. So if you would have remembered when I showed you guys the flavors of the stars, the smaller ones because their lifespan is longer, they actually take longer to form, because the material around them isn't as much as what I showed you in the pictures, because it all depends on what material is available and how much it's gathering. The bigger it gets, more material it tries to gather, and the faster the temperature in the core of the star actually gets to ignite the hydrogen. And then the process is almost kind of a runaway process where it just keeps igniting more and more. And so when you're bigger, your lifetime is small. And when I talk about a smaller lifetime or a shorter lifetime, I don't mean like few seconds. It's still millions of years, but in the whole entirety of the universe, if you look at it, that's a very, very small fraction of time compared to the other objects in the sky. But they form all the time. The process is longer. So almost at every point you're talking, there's new stars forming at every moment. It's just that the process is so slow for us humans because of our timeline. but in the timeline of the stars, it's very, very quick for massive stars and slower for smaller stars.
The universe is so big that pretty much something's happening anytime. Anything you can think of, it's happening somewhere right now at this very second, which is very cool.
Exactly, yeah.
You mentioned star lifetimes, and so I just want a quick follow-up. For our sun, which is a star, how long has it been alive and how much longer does it have to live?
So 4.5 billion years approximately is what we call, how long the sun has been around. It's going to stay in this state around for four more so billion years before it starts to go through a phase when it's going to start to expand and go to this path where it's basically is going to end up in its death. I don't like to call it a death, but it goes through this phase where it ends up then being a white dwarf, which is kind of the last phase of a star for a size like our sun. And so that entirety, after the 4 billion years, there'll be a few more billion years before it gets to the white dwarf phase. But, we have around 4 billion years to figure out another planet to live. Because it's going to start getting hotter and hotter here, and then the sun is going to swell, and it's going to do this lovely dance of swelling and contracting back, and then swelling again. So yeah, 4 billion years.
We've got some time. That's good to hear.
Yeah.
All right, I'm going to take 2 questions each from each class. So we'll start with Miss Wood's class. We'll come up to you guys, and then we'll go right back again for a second question, and we'll do the same with Miss Saunders. So yeah, come on up, guys.
Go ahead, Anthony.
Do stars orbit?
Yeah, so 2 stars can orbit each other. They're called a binary system. And they're actually one of the most common ways. So most of the stars that you see in the night sky are actually binary systems. And it's interesting because, our sun is not a binary. And so it's very hard to imagine, 2 stars and then planets around one star, and you have these 2 stars rising and setting and stuff like that, but it's very common to have a binary system, and it's not like one star is in the center and the other one revolves around it. It's actually both of them going around each other. So the dance, if there was a way to speed up the time and see them going around, that would be pretty cool. Luckily, we have computers for that, so we can do that in the computers and see what the motions of these objects are. You can also find a triple system where you have 3 stars going around each other. There have also been found quadruple systems where you have 2 stars, and then you have 2 stars, and then all 4 stars are going around each other. However, as you get more and more stars, it becomes more and more chaotic. So, at some point, that triple star system, one of them is going to be kicked out, and it's going to end up being a stable 2-star system, and that third star is going to be like the lonely one. But it's pretty interesting, neat dynamics that goes on, and a lot of the stars that you see in the night sky are actually binary systems. So that's pretty interesting.
Very cool. All right, Ms. Wood's class again, if you guys have another question. By the way, I like the student with the NASA shirt. I don't know if that was intentional, but it's awesome.
Daniel, you. Okay, but what's your question? Go ahead. Go ahead.
When a supernova happens, is there leftovers of the star?
Ooh.
Yeah, really good question. So a lot of the time when supernova goes off, you can either have a neutron star that's a leftover, or you can have a black hole, which is super interesting object and a mysterious object. There's definitely material that's shed out. So you have a massive star like the O or B type star that I showed you guys. They end up either being a neutron star or a black hole. And what happens is during the supernova, you have material that is, basically expelled into space, and then you have a core that's left. And depending on the size of the original star, you can either get a neutron star or a black hole. So we do always have a leftover, and it just depends on the mass. And I do want to point out to the NASA shirt, I'm actually wearing David Sinjak t-shirt right here. David actually went to space earlier in the year, and when I got to go to the museum, I bought myself a t-shirt with his patch. So
Yeah, and so if you're one of the classes that wins the trip from an astronaut, I don't know if it's going to be him personally, but Canada has 4 astronauts. They're all exceptional people, so that's a really neat opportunity. Again, I'll pass that when we're done. All right, we've got a couple questions from YouTube. So we've got Mr. Richardson's class in Hoover, Alabama, wanted to ask, what is the greatest, what played the greatest role in you pursuing the path you've chosen as an astrophysicist?
Really good question. I think there were 2 factors. The fact that how mysterious space is, and it kept drawing me towards it because there were so many things that we did not know about it. But I think if I think of one particular moment that kind of ticked me towards this was that looking at the night sky using my own telescope. It's not on everyday basis. I didn't own a telescope until I was around 12 or 13. But when I did, I could actually go and look at the moon, the Saturn, Jupiter, all these planets from my own telescope, and I was like, wow, these are interesting, mysterious objects. We see the moon on almost like everyday basis, but like you don't get to see Saturn and its rings, and you don't see Jupiter and its moons just with your naked eye. So that it was just a tipping point, being like, I think this is cool, right? Like to study these things. So I ended up being like, all right, this is what I want to do, and this is what I want to go.
Very cool. I urge the classes, so both of you guys are in areas where the Royal Astronomical Society of Canada operates, and so they bring telescopes so you can see things like Saturn's rings. So just get in touch with your local chapter. They're amazing people. We can help with that too if you'd like any help, so just email us about that. But it's a really exceptional opportunity. So, and it inspired Dr. Patel. So there you go. All right, we've got Mr. TC from Bristol Road Middle School in Mississauga, and they wanted to ask a question about the James Webb Space Telescope going up in either next year or a couple of years. What are you most looking forward to finding out from it once it gets launched? And can you explain to the classes that are here what it is?
Yeah, so James Webb Telescope is kind of the successor of Hubble telescope. So I showed you guys a picture of these lovely proploids, as we like to call them, or young protoplanetary just surround these stars. And Hubble is powerful enough. It is obviously in space, avoiding all the atmosphere and all the pollution that we have here. And it's looking at the universe. And what I'm really personally really excited about the James Webb, that it's bigger, it's better, with better technology, obviously. And I'm looking forward to seeing just more pictures and wonders like I have in the past. So that picture of the Orion Nebula, those proploids, better, sharper images of these objects, and just, you helping scientists like us to solve more mysteries is what I'm actually looking forward. So, if I can get better pictures of those proploids, that's the best thing.
Well, I mean, for the students that are in these classes, they've grown up in a world with the Hubble images. So they've seen things like the nebulas you show, but we didn't have any of that when we were much younger, and certainly your teachers wouldn't. And so it's so exciting to have a new mechanism to explore the universe. It's fantastic.
Definitely.
And if you guys are interested in James Webb, by the way, we did a session earlier this month with Natalie Hulette, who is a James Webb Space Telescope ambassador for Canada. So really fantastic stuff, and I urge you guys to check that out as well. All right, Ms. Saunders' class, let's take 2 more questions from you guys. Come on up.
Hi, my name is Jackson. What is your favorite star?
Hi, that's a really good question. I have had a hard time figuring out what's my favorite star because believe it or not, during my 4 years of research, I studied 4 stars. It is so interesting that almost like I would spend a year studying each star. I think I would put like a category to it rather than one particular star. I mean, I love our sun. It's great. We're here because of the sun. But I really do love the most massive O-type stars just because, they're massive and so mysterious. So, if I were to pick the category out of the flavor of the stars, I think the O-type, because being so mysterious, would be my favorite.
Now, just really briefly on the O-type stars, you showed us the picture depicting them size comparison to each other. Is there a way to think of like the moon versus the Earth? Is there a way to think of the sun in comparison to one of these stars that kids can visualize, like a golf ball to a basketball, or what?
Yeah, so imagine, I generally do with our sun. So, you saw the G-type stars. So that's, imagine that's this size. O and B type stars start anywhere from 8 times. So if you have a big bag and you put 8 of those together, that's how the most, I guess, the least massive ones of those O and B type stars would be. But they could go to 10, 20, 30 times. So, take our sun and put like 30 of them in a bag. That's how big and massive they would be. So, it's very hard to imagine these stars just because of the scale. I mean, imagining our sun compared to Earth is already a big thing. And imagining these stars, compared to these, it's huge numbers. So I always like to use our sun as kind of the standard for these stars, and say 20, 30, 40, 50 times more massive than our sun.
Excellent. Very cool. All right. And back to Miss Saunders' class. Thanks so much. Come on, guys.
Hi, my name is Annie, and my question is, because we are the closest planet to Mars and it's the closest to us, and we've been researching it for so long, how come we haven't been there yet?
That's an amazing question, Annie. We have, when we stepped onto the moon quite a while ago, 50th anniversary just passed, we thought we would be on Mars by now. But there are a lot of things that are different for Mars than it's for Moon. Moon is closer to us, and it only takes a couple of days to get to the moon. It takes almost at least 6 months to get to Mars. So you can imagine if I were to pack 6 astronauts right now in almost like a tin can sized, a house-sized spaceship and send them to Mars. There are a lot of things like we don't know how psychologically they're going to feel, because when we send them to Mars, 6 months getting there, we obviously just don't want them to get there and come back. We would want them to stay and do some science. That would be a couple of years, and then coming back. So it's almost going to be 3 to 4 years trip that they're going to do, that they're going to be away from home, that they need to have all resources with them when they're going to be there. They also need to have all the instruments that they're going to work on in terms of sciences. But I think we could, at this point, deal with all of those things. One thing that we really, really, really need to figure out in the next couple of decades is going to be how we shield them from the radiation of the sun. So right now here on Earth, we're protected by by Earth. We have an atmosphere, and above the atmosphere, we have these lovely magnetosphere, which actually traps all the solar radiation that can be harmful to us. When we go to Mars, we don't have that sphere with us anymore. So we will be bombarded by a lot of radiation when we go there. And so we need to figure out how to protect the astronauts when they get there. And so that's kind of one of the key questions. Once we have that, there are a lot of other things, like how would they be psychologically dealing with being away from home? How would they be replenishing their resources? Do we have that kind of technology to be sending them for such a long time, being there by themselves, launching back and coming back to Earth in that 3 or 4 year time frame? So there are a lot of these different small things that need to be figured out. I think solar radiation is probably one of the highest critical thing that we need to resolve in order to help send humans to Mars. But I'm hoping that in your lifetime, it's going to be your generation that's going to actually be going to Mars. So I'm hoping you guys will be helping in solving us all of these mysteries to then be able to send humans to Mars.
And if you go to space camp in Quebec, you can start out right on the path. No, but
Exactly.
it's a really great, I'm really glad we got that brought up. Because I mean, going to the moon was the biggest technical challenge humans have ever accomplished. And the Mars is a different order of magnitude. Like, it's so much harder, so much further, so many new challenges. So it's a fantastic question. And thanks so much, guys. All right, Parshati, before we wrap up, as we've covered a lot, and again, time flew here, is there any last message you want to share where kids can find out more about what you do, about Western Space, junior astronauts? I mean, I'll pass along the links, but how can kids keep engaged and excited about space?
Yeah, so I would say always ask a lot of questions, and if you need an expert, feel free to reach out. Definitely Explore by the Seat of Your Pants is one of the ways, Jesse, you can connect you with tons of experts. We love answering questions all the time. Something that put me to the path of where I am today was I just kept asking questions all the time. My parents got fed up and brought me books, and they connected me to experts, and I got to ask my questions to them. There is there's always an ample opportunity to go and discover things yourself as well. Now with the internet and libraries, you could do that all the time. So I would encourage you to go and sort those resources and use them wisely. And if you ever have any questions, I'm more than happy to answer. You can connect to Jesse and he can pass on those to me. And if there are other things that I may not be able to answer, I can always connect you to the other experts in the field as well.
Outstanding. And so we'll do that. I know that we always have more questions that we can possibly cover in a session, but if you guys have any extras, send them in an email to me. I'll pass them to Dr. Patel and we'll go from there. All right. Well, how every one of these sessions ends always is I'm going to demute both classes' microphones. So Miss Wood, Miss Saunders, guys, if you guys could join me in saying a huge thank you to Dr. Patel for joining us today. You're both demuted. Awesome, guys. So yeah, check out for that email. I'll send a whole bunch of things that you guys can use to learn more. And thanks so much for taking part today and for our Space Month. Dr. Patel, thanks so much for joining us today.
Thank you for having me. Hope you guys had fun.
All right.